a sequence of primes do not scream out any pattern and make any sense at prima facie, right? And therefore, there do not exist theories or formulas revolving around prime numbers. But what cannot be achieved through pure mathematics can be through computation. So, a lot of efficient yet very simple algorithms like checking if a number is prime or finding the prime factorization of a number or even finding all the prime numbers up till some limit have been devised. And you literally find problems based on them in every third contest. They are that probable and important. So we'll be looking at all of them, but for this one, we'll restrict our goal to test the primality of a number. So let's jump straight. So how do you check if a number is prime or not? Well, all we have to do is the way we do it on a pen paper. We have to convert it into code, right? So what we do is we simply loop through all the numbers from 2 to n minus 1 and we check if n is divisible by them. Basically, if we find any factor of n, I, so we can say that the number is composite, otherwise it is a prime. So as a pseudo code, what we do is we iterate I through 2 to n minus 1, right? And then what we check is if I divides n. If yes, then we can return false, right? Or return composite. Otherwise, if let's say we are not able to find any divisor of n, right, even after the loop, so we can in that case return that the number is a prime. So this is the naive way to approach it. And can we do something better? Well, let's have a look at that. So consider all the factors of any number, let's say 36. So we say that 36 can be written as 1 into 36 or 2 into 18 or 3 into 9 or 3 into 12, sorry, or 4 into 9 or 6 into 6 or 9 into 4, then 12 into 3, 18 into 2, and you also have 36 into 1, right? So this is like a set of all the ways in which 36 can be represented as product of its factors. So that's evidently you can see this that a factor always exists in a pair. Like here for 4, the other number, that is like if a is 4, let's say a is 4. So we can say that the other number, that is b, is obviously 36 by a only. So this is b. So if a is a factor of 36, then I can say that 36 by a, that will be b, is also a factor of 36 automatically, right? 4 is a factor of 36 and 36 by 4, that is 9, its cofactor is also a factor of 36. So factors always exist in pairs. So I can write a into b is equal to n, right? Or in other words, to remove the term b, we can write a into n by a, which will essentially be b only, right? This is equal to n. So if we revise the problem that we are given, what we in the absolute terms have to see if a number has any factor a or not, right? So we do not basically have to search for b, we only have to search for a. And considering that I put this condition that a is less than or equal to b, so that we are only considering unordered pairs, right? What I can simply do is I can remove the duplicates from this set as well. So 9 into 4 already has a duplicate of 4 into 9 above, so I remove it. 12 into 3 also has a duplicate, right? 3 into 12. And basically this is kind of a mirror of the upper half, so I can remove all these because they have a duplicate above, right? So this is my new set now, which is like a unique set which does not contain any pair repeated again. So unordered pairs. So now can you see that what's the last value that A is taking? A is equal to 6 at max, right? And which is nothing but square root of 36. And we can do this mathematically as well, that let's say if A is greater than square root of n, so because B due to this condition is also greater than A, meaning it's greater than square root of n, so something greater than square root of n multiplied by something greater than square root of n can will always be greater than n, right? So for this equation to hold true, A into B equals n, where A is less than equals B, the maximum value that A can take is obviously square root of n, right? And since we are searching for A, we can say that instead of looping through 2 from basically till n, if we simply loop till square root of n, then it is as good as looping till n, because anyways the maximum value of the smaller cofactor will be square root of n, and we do not basically need to consider the bigger cofactor, because anyways we just have to check if there exists a factor or not. So if we have any one of them, then automatically there would exist its cofactor also, that is for A it would exist n by A, or if we take B then it would exist n by B, right? So even if we check for one, the other will automatically exist or not. So simply searching till square root of n is enough. If we find a factor till square root of n, then it's a composite number. If not, then it's a prime. To simply, instead of going through this range, right, this is the incorrect range, the slower range basically. From instead of this, we go till 2 comma square root of n, right? So this is the algorithm, a fully functional 100% working algorithm that you can apply anywhere. It's not that in 90% or more of the cases it will work. It will work for every case. So now let us write some code for it as well. So I'll move on to the CodeChef's online IDE, and now let's start coding. So I'll first take the input for n, right? And then what I'll do is I'll run a loop for int of I is equal to 0, and let's basically create a function, a boolean function is prime, that takes a number n, right? And it will return if return true if it's prime and false if it's composite. So let's move our logic from here and simply output yes or prime if it's prime, right? If is prime n, in that case prime, otherwise composite. Okay, so now let's start off with the loop. So what we do is we loop from I equals 2 till I into I is less than equals n. So like basically I goes till square root of n, but since in C++ we can write such explicit loops, we can do this, and this basically prevents the use of that square root function, which could sometimes yield some wrong results. And but in Python you can basically use the square root function itself, where you have where you cannot do something like this, right? It's an implicit loop that simply takes, for you can basically write for I in range 2 comma square root of n plus 1, right? But in C++ we can do this, so this is a bit more readable. And now what we'll check if n is divisible by I. In this case we are going to return false, and if we do not return anything, then we are going to return. So now let's run it on, let's say, the custom input 10. Okay, so basically we need to enclose this in round brackets, right? So let's run it, and for 10 we should get composite, and yes, we are getting composite. Let's change this to a prime number, let's say 23, and for 23 we should be getting prime. So yes, we get the result prime. And yes, this is the algorithm for this. This wraps up the video. If you learned something new, then make sure to smash that like button. And if you have any queries, then you can, as always, leave down in the comment section. This is Bharat Singla from CodeChef signing off for now, and I'll see you next time.